Okay, so welcome to the last leg of our little tour of problems and situations where greedy algorithms in fact do not work. So to demonstrate a situation where the greedy approach fails rather dramatically, I have picked the traveling salesman problem. You may have heard of this problem before, given that it's a classic and famous optimization problem, but nevertheless, let's begin by looking at the definition. So in this problem, you're given a list or a set of n cities or locations, and you're also given the costs of traveling between any pair of these locations. In the symmetric version, you might assume that the cost of traveling from A to B is the same as the cost of traveling from B to A for any two cities A and B. And in the asymmetric version, you drop this assumption. So the cost of going from A to B may be different from the cost of going from B to A. This can happen, for example, in applications where you have some one-way roads between locations and the situation is truly not symmetric. Notice that these costs may not always reflect necessarily physical distances. The costs may be more abstract or may be based on other things like the costs of actual airline tickets and things like this. So in particular, the costs here may not satisfy things like the triangle inequality. So it may be cheaper to go from A to C by going through a detour, unlike what would be intuitive if these were really physical locations in a plane, and let's say that the costs were reflective of their Euclidean distances, as is the case in this example, which is essentially a recreation of the example on the Wikipedia page for this problem. So assuming that the costs between any pair of points is just proportional to the Euclidean distance between them on the plane, then the tour that is being drawn out right now is the optimal one. So just to make our setting a little bit concrete, let's say that we are working with the symmetric version of the problem, wherein the cost of going from A to B is the same as the cost of traveling back from B to A. Further, let's say that we do not have the triangle inequality, so the costs are arbitrary and they don't come from any underlying distance metric or anything like that. Let's also say that the costs are not bounded in any way, so these could be arbitrary numbers. We do not assume, for example, that the costs have to come from the set 1, 2, 3, 7, 10. It's not like that. So this is a fairly general version of the problem. Notice that intuitively, the more restrictions you put on the problem definition, on the setting of the problem, the easier your job becomes as an algorithms designer, because the hope is that you can leverage these extra assumptions and use them to your advantage when you're coming up with an algorithm. But you can imagine that your life as the designer of counterexamples to greedy approaches may become a little bit harder, because the more assumptions you make about the setting of the problem, the less wiggle room you have while you're constructing your counterexamples, because you're now constrained to operate within these assumptions. So hopefully that bit of intuition made sense. And as I said, the choice of assumptions that I just described are relatively arbitrary, and I would welcome you to play around with a different setting and see what you find. Now, if you're interested in the traveling salesman problem in general, then the good news for you is that this is very much an active topic of research in computer science. In fact, there was a paper that appeared in 2020, which is quite recent at the time of this recording, and it gives improvement that has been long sought after. And despite the fact that the improvement may appear to be small from reading the abstract, it caused much excitement. And if you want to get a sense of the excitement that it generated, I would really encourage you to read this article that appeared also recently at the time of this recording in Quanta magazine, covering mostly the development around this paper, but also covering a lot of interesting history and trivia about the problem. So this tweet about this article really reflects the sentiment of computer scientists around traveling salesmen. It shows how deeply we care about it and how fundamental the problem is to the field at large. Of course, Traveling Salesman is also a bit of a cult classic. It's made its way into XKCD Comics and other popular culture. So if you look at the description of this video, you will find a few links that you might want to look at if you are curious about the problem beyond this very short discussion. But let me just pause here and talk about what would be a natural greedy approach to traveling salesman, right? So you're sitting in your origin city and you're thinking about planning your travels to the N cities on your list, the remaining N minus 1 cities on your list. And of course, you plan to come back once you're done. And the natural thing to do is to perhaps just look at what is the cheapest city to go to from the one that you are at currently. So in the first step, from the origin city, you just find the closest city in terms of cost, the cheapest city to go to next. And once you are at that city, you just repeat this exercise, making sure that you're only considering cities that you haven't already visited as you go along, except for, of course, when you're done, then the last move is forced because you have to come back to the origin. So at any intermediate point in your travels, just find the next cheapest city to travel to that you haven't visited already. And then when you're done visiting all these cities once, then at the very end, you just pick up the ticket back to the origin city. So that is the greedy algorithm. And I would encourage you to think about whether this would work. Given the nature of this lecture, you already know the answer. But what I would encourage you to do is pick up some pen and paper or whatever your favorite way of thinking is. And just try to come up with a concrete counterexample for this approach before I show you one. Okay, so here is a specific example from the book Design Methods and Analysis of Algorithms. And if you look at the costs here, let's just try to run through what would happen if we applied the greedy algorithm with the origin city being the city on the top left, which is the city labeled A. So from A, the most accessible city is B, and it's a cost of 1 to go there. From B, you have two possibilities. You could go to D or C. It's cheaper to go to D, so that's what we will do next. From D, you cannot go to A, you cannot go to B. These are cities that are already visited. So you pretty much don't have a choice at this stage, and you have to take this rather expensive edge to C. And from C, of course, you return to the origin. So the total cost of this tour that is inspired by the greedy strategy is 9 units. If you add up those numbers, you see that it's 5 plus 2 plus 1 plus 1, adding up to a total cost of 9. Now, once again, this is a good place to pause the video and think about whether you can beat the outcome of the greedy strategy. Is there a cheaper tour? And if yes, by how much? Okay, so hopefully you had a chance to think about this. And it turns out that in this example, the greedy output is indeed suboptimal, and you can do better. And here is, for instance, one way that you could do better. So starting at A, instead of being distracted by the most tempting option, which is to go to B, let's take a locally suboptimal option, which is to go to C first. So we go from A to C, and from here we go from C to B, and then from B to D and from D to A. These last two moves are essentially forced. But now if you look at the total cost of this tour, it's going to be 2 plus 2 plus 1 plus 3, which is 8, and which is better than the tour that we had from the greedy approach. Now, you could think about whether we could do even better. You could think about coming up with examples where the gap between the greedy answer and the optimal answer is perhaps larger, because here it seems like just a tiny improvement. So you could play around with that aspect of this as well. And if you remember in the beginning, I sort of said that greedy fails quite badly for this problem, and there are many ways of quantifying the idea of how badly greedy fails, or even the idea of whether a greedy algorithm can be salvaged. So in some situations, although the greedy algorithm may not get to the optimal answer, it may get to something that is close to optimal in a way that you can actually prove. So these would be greedy approximation algorithms, and they are quite common. But the comment we are going to make now is going to be in a different spirit, and it's a remark borrowed from the introduction of this paper, which is titled When the Greedy Algorithm Fails. And if you're curious to actually look up this paper, you can find a link to the PDF in the description of this video. But here is the comment which I wanted to bring to your attention. So it turns out that there are instances of TSP that you can construct which are such that the space of solutions is abundant with many optimal solutions, and yet somehow the greedy algorithm will end up finding the unique worst solution. So notice that there's just one worst solution, and the greedy algorithm will end up finding that one. And you can also ensure that the magnitude by which the solution is worse than the optimal ones is rather large. As you can tell, you can make it as large as you want it to be. So this is the sense in which we meant that not only does the greedy algorithm fail, it's not that it misses the optimal solution by a whisker or that it fails occasionally, but this quantifiably demonstrates that you could construct instances, arguably artificially, on which the greedy algorithm can be as bad in its performance as you want it to be. Now, all this is not to say that one must completely disregard greedy approaches, even to TSP. It's conceivable that there are subclasses of instances where the greedy approach performs okay, or perhaps there are other heuristics which are a more sophisticated mix of greedy-inspired strategies and other common sense pre-processing that works well in particular situations. So there's definitely been a lot of work along these lines, and you can find out more about it if you were to even read the Wikipedia article on Traveling Salesman. But the larger point that we really want to drive home with some of these discussions is the fact that you have to be especially careful with greedy algorithms, simply because it's this dangerous mix of looking like a very tempting approach and seemingly correct, while you really do need a formal proof of correctness before you can be absolutely sure. I mean, this is true for any algorithm that you come up with, but greedy algorithms can be especially slippery, and we just wanted to make this warning a little bit explicit through some of these examples. Now, I'll just repeat something that I did say at the start of this week as well. If you're in the middle of a contest and you're working on a problem for which you have a greedy strategy that appears to be very convincing, but you don't have the time to prove it rigorously, and let's say you have tried to think of some quick counter examples but you can't seem to find one, then it might be a good idea to just code it up and see if you get lucky with the judges. This would make sense to do, especially if you're not penalized for wrong attempts, and it's just a quick sanity check. If nothing else, at least you eliminate an approach, and it's usually doable because greedy algorithms tend to be simple enough that they can be implemented quickly. However, at least when you're up solving or you do have more time, I would definitely recommend actually going back and trying to confirm why your algorithms worked whenever they did. And of course, if they didn't work, then you probably have eliminated an approach and you can move on to the next set of ideas. So that's useful as well. So with that, it's going to be a wrap for week 3 on greedy algorithms. I do hope that you found some of these discussions useful. Of course, as always, we will keep the conversation going on the Discord community as well as on the Google Groups mailing lists. So please do send any questions or comments or suggestions over there. Also, feel free to leave your comments on this YouTube video, especially if you're watching this video outside an active run of this course. We always look forward to hearing from you. Thank you so much, and we will see you next week. It's bye for now.